We're very happy to have Sinai Robins from the University of Sao Paulo telling us about new approach to counting points in rational polytopes.
Yeah, thank you, Sam. Thank you, Kim. Thank you very much for the invitation. It's great to be here. I've never been here before. It's kind of so a lot is going on recently. But let me. How do I change the slides here? I guess, right? Yeah. So I guess I'll stand here for the moment. Then I'll use the board a little bit later. So I keep revisiting this topic. In fact, in the last year, I've been doing something else, some Fourier perspectives on polytopes. But then I came back to this topic of integer points in polytopes because something came up unexpectedly in November of last year, and then more so this year, so in January and February. So I'll talk about the genesis of this field and take you through the field a little bit and up to the present. Let's see, to count, so I guess I use this here. We'll talk about motivation, discretization. I'll talk about all these topics. And the two main new topics in Ehrhart theory now, from this perspective anyway, are discrete moments. There are these discrete moments which I'll show you how they come up. Discrete moments of integer parallelepipeds, which sounds simple. And then the lattice flows on the flat torus, which is a very classical and very simple dynamical system. It's probably the simplest of all dynamical systems. And it comes sort of unexpectedly at the vertex of each polytope. So I'll show you how that comes up. So even though it's the simplest of all dynamical systems, it's somehow still complex when you sum over that flow, you sum certain polynomials, and there are a lot of open questions that turn out to come up in the last 6 months. So classically, we start with integer polytopes, so integer polygons in particular. So just to get everything out of the way, an integer polytope has vertices which are integer points. A rational polytope has vertices which are rational points, and we're in Euclidean space. And so in integer polygon, we dilate and count, and I always seem to be dilating and counting, as Rich would always say. So if you dilate and count, in the 60s, Ehrhart discovered that you get some very beautiful structures. And so a motivating question is how do you discretize volume? How do you discretize area? There are many ways to discretize, infinitely many ways to discretize. You can put various different weights at the integer points, including local solid angles, local intersections with small balls of radius epsilon. And so there are many different ways, but one very classical way that combinatorialists like in combinatorial geometry is to just count. And so if you just count, you can define the discrete volume to be the number of points in a dilate. So you dilate by an integer t, classically, and then you count. And when you dilate by an integer parameter t and count, Ehrhart showed you get a polynomial for integer polytopes, and you get a quasi-polynomial for rational polytopes. So let me remind you a little bit of his results, classical results, and then we'll see the new stuff. So classically, it's very easy. You start with an integer polytope in the simplest case. You dilate by an integer. You count to get a polynomial. These days, it's been called the Ehrhart polynomial since the 1960s. And Ehrhart, late 50s actually, he showed that you do get a polynomial when you start with an integer polytope and you dilate by an integer. He also proved, and by the way, the coefficients are they're invariants of some sort. They're not complete invariants, but they do form invariants for certain valuations on the space of polytopes. And so, for example, the leading coefficient, this is trivial, it's the volume, an asymptotic argument immediately shows it. The constant term is 1 for a convex polytope. For a non-convex polytope, the constant term will be the Euler characteristic. The codimension 1 coefficient, CD minus 1, turns out to be the surface area, but normalized with respect to the lattice structure on each facet. So each facet goes through a d minus 1 dimensional lattice for an integer polytope, and relative to the fundamental domain of that sublattice, you divide by that fundamental domain, and you get CD minus 1. So it's a surface area normalized with respect to each sublattice and each facet. 1/2 times 1/2. So the codimension 1 coefficient has been known for a long time. The other coefficients somehow measure the case skeleton, something enumerative about the case skeleton. So intuitively, so for example, C1 will measure something enumerative about the 1 skeleton of the polytope. The most complicated coefficient turns out to be C1. As you go down, it gets more and more complex and very interesting. So many people have studied this over many years. Yeah, so that's what we talked about Ehrhart. He already proved that back in the 50s. And he also proved this even more important result that involves periodicity. So this now gets more interesting. When Ehrhart proved this, it was in the early 60s. Ian McDonald also came in and proved some things. So if you have a rational polytope and you dilate by an integer parameter t, Ehrhart proved in the early 60s that these coefficients are periodic functions of t, and the smallest period is an open problem today, and it leads to many different things. The smallest period is not known, but some periods are known, and this is called a quasi-polynomial. So a quasi-polynomial meaning the coefficients are not constants, they're periodic functions of t. Okay, so far so good.
But the periods are going to be different for different cases?
Yes, for different polytopes, you mean, or?
No, the coefficients are periodic.
Different periods, right. So, yeah, so that's right. So they have different periods. Sometimes one of the coefficients turns out to be constant when it shouldn't be. So you don't expect, for a general rational polytope, it's not going to be constant. But when one of the coefficients is constant, it's called period collapse. So there's a whole literature on this, on period collapse. When one of the coefficients is constant, complete period collapse is when all the coefficients are constant, and really they shouldn't be, in a sense that one does not expect the period to be, so you don't expect no period, you expect some kind of period. And so when there is period collapse, there's in fact equidecomposability theorem, and there's an equidecomposability conjecture, an analog of Hilbert's third problem, for a different group though, not a group of isometries, but a group of unimodular transformations. So there is an active field of study about equidecomposability under unimodular transformations when complete period collapse happens. So that's a different thing, and maybe I should have geared my whole talk to that kind of stuff, but I geared it to something else. Yeah, but it's a fascinating field of period collapse, and when a rational polytope feels and smells like an integer polytope, maybe it's equidecomposable to an integer polytope. That's the feeling.
In the case of integer polytopes, the polynomial is invariant under the action of the SL and C?
Exactly.
Yeah.
Exactly, yeah. And that's it's straightforward to prove, right?
Mm-hmm.
In fact, the coefficients are as well. Yeah. Okay, so there's a lot of research about, so there's a fascinating field here that under the surface, but let's, to get back to the history, and then maybe we should make one of these, maybe I should make one of these problems on a problem session today about this equidecomposability, because this seems appropriate here. So one of the main things that has kind of attracted me to this field, so I seem to be always coming back to this, is this kind of question, is there a very explicit form that will enable us to prove all of these results as special cases? And that suggests the question, we should be honest with ourselves, what is a formula? And so here's a formula, I just add 1, and so that's a formula, right? And so it is a mathematical joke, but it's important in some sense to ask what is a formula? So if you just add 1 for every integer point, you get a formula, but that's not very useful. It's accurate, but not very useful. So what is a formula? So, well, it's a subjective thing. To me, a formula is something that gives you insight into structure, some hidden structure, and also there we say efficient. So I would like a formula to also be efficient in some way, but first and foremost to give us insight into some structural data and properties of the object, but also, yeah, also at the end to be efficient. So, examples abound. So the simplest possible example is the unit square, perhaps. If you dilate by t and count, you obviously get this polynomial, and then you ask what are the other polynomials? This is the simplest possible example. If you do it for an arbitrary triangle in the plane, already it's much more interesting. If you do it for an arbitrary three-dimensional integer simplex, already it's very, very complicated. And there was a PhD in 1993, Jamie Pommersheim, whose whole PhD, and it's a brilliant PhD, was devoted to this three-dimensional integer simplex, but also extensions of it using toric geometry. So there's an approach using toric geometry and algebraic geometry, Todd classes, and so on, and it's linked very much, but today we'll talk about a very elementary approach. So a d-dimensional polytope enjoying the property that each of its vertices shares exactly d edges with its neighboring vertices is called a simple polytope. Maybe we should get these out of the way. What is a smooth polytope? A smooth polytope, again, comes from toric geometry. A smooth polytope is an integer polytope such that at every vertex, it's simple. There are exactly d edges emanating from it, but also those edge directions form a basis for the integer lattice. So the matrix formed by those d edges is an SLDZ matrix. So if that matrix is SLDZ for every vertex, that's called smooth. Its corresponding toric manifold is non-singular. Okay, so I don't have usually it rotates because, but anyway. So there's a dodecahedron. That's a simple polytope, for example, because every vertex has degree 3 in R3. The octahedron, which is the cross polytope, is not simple because in R3, the vertices have degree 4. So by the way, the octahedron and the cross polytopes are in many ways the worst possible polytopes in every dimension, in the sense that whenever you have some nice classification of, well, I'm being too general. Many nice classifications have to always omit these guys. So they're kind of the worst. For example, if you want to tile space by translations, if you want to say which polytopes tile by translations, these guys kind of leave the most room. They're kind of the worst density objects if tiling by translations and so on. And
did you say cross polytope?
Yeah, the cross polytope. Oh, so the cross polytope. If you do functional analysis, it's the unit ball in the L1 norm. Or if you like, it's you take the standard basis vectors E1, E2 up to ED, take plus or minus the standard basis vectors, take the convex hull. The same thing. So that's the cross polytope. Let's go back to very basic things that are easy to visualize. In 2 dimensions, here's an integer polygon. And by the way, I didn't use AI for any of this stuff. Although, for the last 4 weeks, I have used AI for the last 4 weeks, and it's a bit surprising what's going on. So it's a discussion we should, it's a discussion one should have, what's possible, what's not possible, and so on. Anyway, so for this stuff, not yet, but for recently, what I'm going to post in a couple of months, yes. In any case, here's an integer polygon. The tangent cone at the vertex is easy to visualize, so we won't go into any of the rigorous definitions, although we can. It's in the paper, but the paper's in the archives, by the way, and I'll upload a new version. But this is a tangent cone, the vertex tangent cone at the vertex V. There are 3 vertex tangent cones. They paste together in a geometric inclusion-exclusion theorem. It's called the Briançon-Graham relation, and when you consider, so very importantly, if you have a simple polytope, then every vertex has a flat torus. There's a compact torus at every vertex, which is this. you take the primitive edge directions. Primitive means these are the primitive integer points emanating from the vertex. So you walk along the integer line until you hit the next lattice point. So the GCD of the difference coordinates is 1. Anyway, you take the primitive integer vectors, you form this half-open integer parallelepiped, and if you identify opposite sides, you get a compact torus. And it turns out that the whole complexity of Ehrhart polynomials comes from a certain flow, which I'll show you. It comes from a certain lattice flow. You take the integer points and you flow them in a certain direction, in the direction of v, in fact. And that flow turns out to encode all of the complexity of, so that's what I want to show you. Yeah, so if you have a simple polytope, every vertex has a compact torus and a finite abelian group, right? The set of integer points inside this half-open parallelepiped form a finite abelian group. And these finite abelian groups are different, but somehow they interact at all the vertices. And the interaction of these finite abelian groups tells you in a way that we'll see in a second, it tells you what's going on. And so if you take this original triangle, take this cone, take this fundamental parallelepiped, and translate it to the origin in the formulas that I'll show you, all of these half-open integer parallelepipeds are translated to the origin, and therefore you get these finite abelian groups.
By definition, why don't you take like half of the top edge with the entire bottom edge?
Yeah, so I wanted to make it half open, so after I identify the sides, it becomes a compact. Oh, the primitivity. Oh, the primitivity is not essential. It just simplifies life. Yeah, you're right. It's not absolutely essential, but life becomes much nicer. And if you're interested about periodicity questions, it also simplifies the periodicity because you're taking the simplest possible, you're not repeating anything. And so to tackle the open questions about periodicity, one wants to take the primitive edge vectors. Was that the question?
Yeah, I guess
yeah. Yeah. Yeah, so here's the translated integer parallelepiped. So for example, in this particular triangle we gave, this is the primitive vector 2, 3. That's the primitive vector 7, 2. We can analyze the points inside the form a finite abelian group. In this case, I think it's a cyclic group. It doesn't have to be cyclic always in dimension 2, but when it's cyclic, nice things happen. But in general, it's not cyclic. And okay, so let me just introduce the basic notation I need to tell you about the results, the recent results. So an integer vector is called primitive. The GCD of the coordinates is 1. The notation that we'll use for the edge vectors, for the primitive edge vectors coming out of every vertex, and to make these results more palatable, I'll just give you the formulas for simple polytopes. Although they all have extensions now to all rational polytopes. You can triangulate every vertex tangent cone into simplicial tangent cones and then apply all these formulas to each simplicial piece. But let me start with a simple polytope. So you have a simple polytope, you have a vertex, it has exactly d edges. Each one has this label. The w's are the primitive edge vectors at v. And now I'll introduce, so let me introduce these Barnes polynomials. So I think everybody here knows about Bernoulli polynomials. So Bernoulli polynomials started with a very simple number theoretic questions, and I think we teach this in our classes. So if you take, you fix n, an integer n, and you want to sum this. Bernoulli showed that you get a certain polynomial, and I think it's k plus 1 minus the constant term. This is the constant term called the Bernoulli number. Something like that. So there's a formula Bernoulli came up with involving Bernoulli polynomials, and so when n is 1, you get the second Bernoulli polynomials and so on. And so you have these formulas, and if you want to in a nice way, this is about 300 years old, I guess, or whenever Bernoulli came up with it. In an interesting way, you can sort of ask, how does this extend? If you want to extend this to summing, instead of summing in one dimension, you can say, well, let me fix a complex vector, let me fix the n, and let me sum these points instead of over a one-dimensional polytope. This is a one-dimensional polytope from 1 to k. I can sum it over a polytope in d dimensions and ask how these linear forms, powers of linear forms, for example, extend this. So in some sense, these extensions are what we're going to do today. So there is some work about polynomials, summing polynomials over polytopes, but I want to show you some new formulas that involve the Barnes polynomials. So in a very direct way, these Barnes polynomials extend the Bernoulli polynomials. If you let the dimension be 1, this is exactly the definition of the Bernoulli polynomials. And so they encode a lot of interesting number theory and so on. So these are the Barnes polynomials. We'll denote the kth Barnes polynomials by b sub k of Ta, and they're polynomials in T. Just like this is a polynomial, as you know, this is a polynomial in N, a polynomial in K, sorry. And they're so they encode a lot of interesting things. Historically, Shintani studied similar things, and they come in Shintani zeta functions and so on, but now they have a different direction into combinatorial geometry. So let me show you the new direction. So this stuff is it's only since January, so I'm kind of trying to see how many open problems we can tackle with these things now. But anyway, so the Barnes numbers, by analogy with the Bernoulli numbers, which are the constant terms of these polynomials, these are the constant terms of the Barnes polynomials in T. Okay. We're going to form vectors of linear forms at every vertex. Every vertex, remember, had the edges are W1 of V up to WD of V. We form this vector of linear forms. Here we let Z be an arbitrary generic complex vector, which we can define what generic means rigorously. I'll do it in a second, but take any complex vector, generic, we have these linear forms. And so it turns out that there's a very, very concise description for the Ehrhart polynomial, which I found surprising in November, which is this. You sum over the vertices, and for every vertex, you have this Barnes polynomial, and you plug the local data of the vertex into the Barnes polynomial. So this is a polynomial in T. This bk of T, this is a polynomial in T, involving the local data, involving this complex vector Z. So Z can be any complex vector. Generic, okay, so generic means it's not orthogonal to any edge. The real part of Z is not orthogonal to any edge of the polytope. So that's generic. You take these Barnes polynomials, and then you have this interesting finite sum, and this is where the lattice flow is. So the lattice flow is you take every point in the lattice, you flow it along the direction minus TV. So you take the vertex V, you multiply it by a real number now, a positive real number T, minus T. So you flow it along the direction minus T, V, minus V, essentially, minus TV. And then you flow it along the compact torus. So you mod out by the torus. And over that flow, you define these polynomials. So you sum these polynomials over the compact torus. And that's all. That's all you need, it turns out. So that's a very... Sorry?
Can you show the definition of A?
Yes, certainly, yeah. So at first I thought... Yeah.
The final answer doesn't depend on Z. That's the point.
Yeah, surprisingly, the final answer does not depend on Z. And I found that to be very strange. I still do. But following the proof, it's very easy to see why. And yet, when you start computing, it's a little bit strange because the Z's magically cancel out. And so the Z, in physics, this happens sometimes, right? Localization. It's still weird to me that the Z cancels out, but from the proof it follows. I guess you can call it localization. But, sorry, what was the definition of the Yeah, so the definition of the A sub v is the vector of linear forms defined by the edges at v. So again, every vertex has exactly d edges, w1 of v up to wd of v. You take an arbitrary complex vector z, take the projection along z, so the dot products, and that's A sub v. Was that the question? Yes. And then this is easy to compute. It's the given data. You're given the vertices and you're given these edges. So given the local data, you know A sub v. Z is a generic complex vector, and that's it. So that's the, I guess that's the first explicit formulas we have after 50 years of Ehrhart polynomials. So it surprised me a little bit, except, so now the question is, okay, so what can you do with it?
Isn't the right-hand side a continuous function of z?
Yes, so
Then shouldn't it be true for all z?
yeah, so this is, oh, why do I have the word almost all? That's the question. It's because of the proof, really. The proof that so I don't know about the complete truth yet. For all, what's that?
You can't just plug in z equals 0.
Oh yeah, right. So that's a good example. Yeah, thanks. Yeah. So if z equals 0, you get, yes, that's true. So, but what other z's can you plug in? I need, at this point, I need z to be generic in the sense that its real part is not orthogonal to any of the edges of the polytope. Yeah, it comes out from the proof, which uses the Brion identity. For the non-generic directions, strange things happen, like 0. 0 is orthogonal to everything. But even things that are orthogonal, if you take z to be an orthogonal vector to one of the facets, also strange things will happen. It won't be true. So, sorry?
What's wrong if z is 0?
Oh, if z is 0, then everything is 0 on the right-hand side.
So this doesn't vary continuously in z?
No.
So why is it not continuous in z?
So I don't know exactly, this is just the truth, right? So it's just, we need z to be generic in order to have equality there.
You reduce modulo phi, right? And that's not continuous.
You reduce modulo? Well, the flow is continuous along the compact torus, but it's not continuous in z, that's right. That's just life.
What is big V here?
What is big, sorry?
Small v lives in big V.
Oh, big V is just a set of vertices. The set of vertices of the polytope. I should take the set of vertices of the polytope. So the sum over V, the outside sum always runs over all the vertices. These are discrete moments of parallelepipeds, integer parallelepipeds. So this is the two new elements in these formulas since January are these discrete moments and the appearance of Barnes polynomials.
So the last sum is an infinite sum?
Everything is finite. No, everything is finite. This is finite. This is the finite sum over the integer points on the compact torus. I'll show you a picture in a second.
So all the sums are finite sum, and you're saying that still the right-hand side is not a continuous function in Z.
Right. Well, at z equals 0, for example, as Rick pointed out, it's yeah. So there's a strange appearance here of this z parameter, and there are forbidden z's, right? But what can you do with it? So, by the way, so this is the so the right-hand side counts for any generic complex z. It counts the number. It's just a combinatorial count. It counts the number of points in the convex polytope. So I know it's peculiar, but by the way, so these coefficients, if you write out the quasi-polynomial as a CR of t, the rth quasi-coefficient, it's not hard to show that it has this form. And this finite sum over the lattice flow, this finite sum, which is it's a discrete moment over the points in this torus. This finite sum also appears here, except for there's an easy identity with Barnes polynomials. There's an identity that if you look at the constant terms, and you take out the constant terms, those are the Bj of AV. You evaluate those constant terms at the local data of the edges. Those constant terms appear in the coefficients. So yeah, so the coefficients, the appearance of z is a little bit interesting. It allows you both the ability to compute, and then at the end it becomes independent of z, also for the coefficients. So each coefficient is also independent of z. Yeah, weird, I know, but let's proceed. So far, so.
Can you use it to get a periodicity, for example?
So I'm trying really hard, yeah. So I've been trying really hard to get for the last few months. I can get some new stuff, yes, but I'm trying to get even better stuff. Yeah, you can use these formulas to get information about the periodicity. And all the periodicity is located in these discrete moments, because that's the only, so the whole periodicity, you can see nothing else depends on t. The only thing that depends on t are these discrete moments. So now everything is localized on these discrete moments of integer parallelepipeds. In other words, flat tori, discrete moments of flat tori. And so it's very pretty, I think, because it's so nice and explicit. It's just that there's still some work to do to get the smallest period.
You're saying this is also not continuous in Z? This formula?
Yes, z is still here. So you take every vertex, you take the inner product of the vertex with z. This is not a Hermitian inner product, by the way. This is just a bilinear pairing. Just you take the formal vi zi, and you take the inner product, raise it to the r, and then you have to multiply by that. Yeah, so. So these are the coefficients. By the way, so I should mention the work of Eva Link. In 2011, Eva Link, she had a beautiful paper where she, for the first time, she analyzed all possible positive dilates. By the way, every theorem here doesn't just hold for integer dilates, it holds for all positive dilates. So Eva Link was the first. She had this very beautiful paper in 2011 where she analyzed in a very combinatorial way the coefficients of Ehrhart quasi-polynomials, and she proved a differential equation. Her differential equation showed that every two adjacent Ehrhart quasi-coefficients have an ODE, and this is a very simple ODE, and yet it was not possible to use this ODE to extend her work because the initial conditions were not known. In other words, it still wasn't possible, but she derived this kind of very surprising ODE in 2011, and from this formula, now it's easy. Using this formula in 2 lines, you can get this ODE. In fact, we can get extensions easily of this ODE to also moments. There are also moment formulas, which maybe I'm not sure if I have them in the slides or not. Hopefully, let's go back. Oh, so if you go back to the compact formula for the Ehrhart quasi-polynomial, let's see. So, right, you can just differentiate with respect to t, and you quickly. It turns out this is a piecewise. This finite sum is a piecewise polynomial in t. As you can imagine, when the lattice point. Anyway, it's easy to show it's a piecewise polynomial in t, and so as long as this flow stays away from the boundary, you can differentiate easily and get her differential equation. So that's Eva's differential equation. It's very beautiful, I think. So let's recall again the definition of the Barnes polynomials. A is a generic. In the Barnes polynomials, the exponents on the exponentials are generic complex numbers, and throughout we let t be any real number. So all these theorems are true for any real dilation, any positive dilation. And in fact, you can extend to negative dilations using something we call Ehrhart reciprocity, so I'll show you. But historically, Ehrhart did positive integers and then extended to negative integers. Now, since the work of Eva Link, we know we can do arbitrary positive reals and then extend it to negative reals using reciprocity, which allows you to look at the interior versus, as opposed to the compact, or the original compact polytope. So now all the complexity reduces to analyzing these moments, these discrete moments, over the lattice flow of a compact torus. So the flow, let me call the flow, you take every integer point, you flow it in the direction minus TV, and you go back, you mod out by, so on the torus, it's a continuous flow, you get geodesics. If the vertices are rational points, then it's a periodic geodesic, so it's one of the simplest things there are, and yet I don't know the smallest period even for one of these things. We know the smallest period for the flow, that's easy, but if you sum a polynomial over the flow, the pieces of the polynomial can interact with each other and conspire to give you a smaller period. So even for one of these, what I call polytope Dedekind sums now, but I didn't want to use the term because it sounds outlandish, even though for one of these discrete moments, I still don't know the minimal period, even for one of them, let alone the sum of them. I think it's doable for one, but still very non-trivial. And I asked the AI last week, and it couldn't do it either. So it's not, but yeah, okay. Okay, so here's an example. So you take every integer point in the torus and you let it flow along this direction. The direction is along the direction of V, which was the vertex of the bottom left. That was the direction according to the original triangle. And obviously, you can see that you get two closed geodesics. One is the purple one, one is the red one. And so it's easy to get the smallest period, but it's not easy to sum the polynomials over the smallest period, over this flow. So everything reduces, the whole complexity now reduces to summing polynomials over this flow. So yeah, the same picture holds for the interior. If you take the interior and you do this whole picture, you also get a corresponding formula. It's almost the same formula. It turns out the only difference is you replace t by minus t, and the only appearance of the periodic structure of t is, again, these discrete moments, polytope Dedekind sums. But this is the only appearance of t that gives you a periodic structure. Here, the t gives you a polynomial structure because of the Barnes polynomials. And so if you replace t by minus t, you get magically the interior. That kind of idea to replace t by minus t goes back to Ehrhart. He showed that if you replace t by minus t up to -1 to the dimension, you get the interior points. And so that's a kind of a fancy geometric inclusion-exclusion theorem. Here we see that the flow just moves in the opposite direction. If the flow moves in the opposite direction and you replace t by minus t in the Barnes polynomials, you get the interior, number of interior. I know it sounds outlandish, but it's true, yeah. But credit goes to Ehrhart originally for observing that. Here we just get explicit forms, that's all. Okay. So there's a well-known reciprocity. This is the Ehrhart reciprocity. If you replace t by minus t up to this power of -1, you get essentially the number of integer points in the interior. Ehrhart proved it for integer dilations. Now we have it for all dilations, and we have explicit forms. So so now I realize since January that this whole picture of Ehrhart stuff becomes fairly easy. It just took me 20 years to realize it, that's all. But yeah, now it becomes fairly easy, and now we can proceed to tackle some of the periodicity questions as well as computational questions which persist, obviously. So you can do things more generally. More generally, instead of summing one, you can sum a polynomial function of the point. So if you sum over the points p in the dilation, you can take these linear forms and sum, these are polynomials in the points. There are also polynomials in the z parameter, but the z parameter is just there for kicks. It goes away. So you can also sum moments. When you sum polynomials, polynomial weights, you get this explicit formula. And again, the complexity reduces to computing these finite moments over points in a parallelepiped. And again, these moments have a reciprocity law, which I won't bore you with, but they do have a reciprocity law, which is new, and it's valid for all real dilates, all positive and negative dilates. You get a reciprocity law, and so on. This one I'm kind of really happy with. So it turns out, so this is a very curious thing. What happens? So initially, it's not so curious. Initially, due to Ehrhart, we know that if you have an integer polytope, the constant term is 1. If you recall, that's from Ehrhart's formula from the 50s. Here, if you just use the fact that the constant term is 1 and apply the formalism that we have for the coefficients, you get this weird, you get an identity that this constant term, which is the left-hand side of the formalism, is equal to 1, which is the Euler characteristic, which we know from Ehrhart it has to be. And then also this is true for all z. Obviously, the z's have to magically cancel away on the left-hand side. And it's true for almost all z. And so it turns out that, as I discovered in the last few months, that this extends a lot of the classical reciprocity laws. So you know Gauss's law of quadratic reciprocity, the Dedekind sum reciprocity, higher dimensional data reciprocity, they all follow from this. In particular, the Dedekind law of reciprocity and the higher dimensional law of reciprocity are special cases of this when you look at right-angled tetrahedra. So if you look at right-angled simplices, both integer vertices and more generally rational vertices, and apply this identity to them quickly, you can quickly achieve all the classical reciprocity laws. So from these closed forms, essentially every classical theorem that I know of now follows quickly, except that, well, there are still open questions, obviously. Yeah, so this is a weird, a very general kind of reciprocity relation. When you specialize to various polytopes, it becomes more explicit, even more explicit than this. And again, the complexity is over here in these finite moments. Here you have a, why is there no appearance of t? Why is the flow not flowing? It's a constant flow. It's because it's a constant term, so we set t equal to 0. To get the constant term, we set t equal to 0, and therefore you have no flow. It's static. Nevertheless, it's an interesting moment over the points, and it's still tricky to compute. All right, smooth polytopes. For a smooth polytope, which means, again, every vertex has edges that form an SLDZ matrix. For smooth polytopes, you have this very simple-looking formula. All you have to do is sum the Barnes polynomials. These discrete moments go away because the discrete moments, by definition, they sum over the integer points in a half-open parallelepiped. For the smooth one, it's only the vertex. And after you translate to the origin, the vertex becomes the origin. So it's gone. So all those discrete moments are now gone, and you just have to sum these Barnes polynomials. So I'm hoping these new formulations for smooth polytopes enable us to tackle some open problems on smooth polytopes. And they do, I think. It's just that the question of one has to obviously work harder to prove some things using these formulas. For a two-dimensional smooth polygon, there's kind of an amusing literature. There's the 12th theorem of Rodriguez and Bjorn Poonen. This might look like the 12th theorem, but it's not. It turns out it's not. It's very different. And so this has to do with something else, although it looks on the face of it like it's the same 12. The 12 comes from the second Bernoulli number. If you look at B sub 2, it's 1 over 6. There's a 1/2, so 1/2 times 1 over 6 is 12. That's where the 12 comes from, just the second Bernoulli polynomial. The Bernoulli polynomials and the Bernoulli numbers persist throughout. This is just a sort of a different, amusing formula that's true for any smooth polygon. So a smooth polygon, again, at every vertex, the two edges form an SL2Z matrix. It's kind of amusing, but I don't know what to make of it other than the fact that it's amusing. here's what happens in dimension 3. You have a 24, and the 24 appears also in extensions of the Poonen-Rodriguez formula. Leonore Gogino, she has some extensions with et al. With some co-authors, recent extensions in the last maybe 5 to 10 years, where she extends these formulas of Poonen and Rodriguez to higher dimensions, but these are different from her extensions. We talked about it and so on, and so somehow they represent something a little bit different. But and again, what's curious about this is if you look at these formulas, and they persist through all dimensions. I won't bother you with the 4-dimensional one. Instead of 1, 2, 3, 4, 5, 6, 7 terms, it goes from 7 terms to something like 30 terms. And then it's super exponential growth in the number of terms. But it's compactly organized by these Barnes polynomials. So if you look at the 2-dimensional smooth polygons, amusingly, again, it's independent of z, but you can see here explicitly that we're not allowed to plug in any z. In fact, you can see that z is not allowed to be orthogonal to the edges explicitly here. So yeah, so that's it. Maybe I should end here. There are many, many open questions. I was going to write like 3 pages of open questions, but let me just stop here with this. Thank you.
Questions?
Yeah.
These examples are coming from your formula?
Yeah, they're new examples, yeah. And I was surprised they haven't appeared before. The closest appearance were the Poonen-Rodriguez formulas, but they represent something else, some other structure, yeah.
But did your formula involve some negative powers of those inner products?
Let's see. So if you look at this, it comes from this. Those formulas come from this kind of stuff, from this counting the number of points in a smooth polygon. It turns out if you look at the constant term, for example, the constant term, and you equate this formula with the constant, you get these formulas that I just showed you in dimension 2 and dimension 3. The negative exponents are embedded in this. This Barnes polynomial is a polynomial in T, but it's a rational function. Yeah, so if you look at the A sub v has these inner products of the edges with z. Remember, so the definition of A sub v. So it turns out by elementary, just definitional considerations, by definition, it turns out these Barnes polynomials are rational functions in the coordinates of A sub v. And A sub v is a vector that was defined by these inner products. Here's A sub v. So as a function of the coordinates of this vector, the Barnes polynomial is a rational function. And that's where the identities come from. That's where the negative exponents come from. Does that make sense?
Yeah. I think that kind of answers the previous question. Because your formula looked like, I didn't know that AV depends on Z.
Yeah. Maybe I should write AV of Z. Yeah.
Otherwise, it looks like a polynomial in
Right.
Yeah, that's right. Yeah. It's a rational function. The Barnes polynomial is a rational function in the coordinates of AV. Yeah.
I feel like in that formula, you could send one of the terms to infinity by sending one denominator to 0 and get some simpler formula, because once you cancel out the poles, things will simplify. I mean, you have this freedom in z. So
Yeah.
Take z special, like close to being orthogonal to one of those, and take a limit.
Take a limit. Yeah.
Cancel, the residues will cancel, and something nice.
Yeah, perhaps. I've taken other special values of z. Yeah, perhaps that's a good idea. I've taken other special values of z, in particular z, to be an integer point. So if z is an integer point, generic and you take the inner products, you can start doing Fermat's little theorem arguments, and you can go a little bit further than Fermat's little theorem. You invoke some elementary number theory, and you can use things modulo 2, for example. So I've looked at mod 2 simplifications of these formulas for integer values of generic z's, and they do give new things, mod 2 formulas, simplifications of various, but it's only mod 2 or mod p formulas. It's not, but yeah, so that's a good idea. Yeah.
One conceptual question. So it's for the Kuhnen et al. Theorem, there is, I forget what the interpretation was, but they give some geometric interpretation of this 12, where 12 comes from. Are there any geometric interpretation of, I guess, your formula?
Yeah, I was trying. Their geometric interpretation comes from, you take the polygon, their polygon doesn't have to be smooth, I think. Mine does. So it's a different thing. But you take their polygon and you look at the polar. If it contains the origin, you look at the polar. And then looking at both it and its polar simultaneously, you can, it's an identity of the simultaneous consideration of the polygon and its polar as you walk around the boundary of the polygon, which is very beautiful and extends to higher dimensions. It's just, this stuff is somehow different. I'm still trying to see what the geometric interpretation of these are.
More questions? Let's
Okay.
again.
Thank you.